Yeah. At this time, we will talk about the diamagnetism and paramagnetism. Basically, when we apply magnetic field in a single atom, and there is a response against applying magnetic field, and basically, when we do not consider for the interaction between spins, and there are two characteristics. One is that Lenz law. Lenz law means that by applying magnetic field in a single atom, point of view, the energy increases by applying magnetic field. Therefore, it is the atoms do not favor to increase the magnetic field energy, but therefore to decrease the field energy. We already know that Lenz law, and there is electronic motion to increase the magnetic field energy, and that is the cause of diamagnetism. And also in paramagnetism is that because single atom has the angular momentum like orbital angular momentum or the spin angular momentum, and the spin angular momentum and orbital angular momentum can interact with the applying magnetic field. That causes the paramagnetism. Therefore, in order to understand the origin of the diamagnetism and paramagnetism, we should take into account the magnetic field response of a single atom. Here, let's start. The first thing on atom, magnetic field. We already know that in a magnetic field there is an electronic spin. Also, the electronic spin has the magnetic moment. This is a spin magnetic moment. There are two possibilities. One is the spin up and spin down, and it is a spin is 1/2. Here, the energy by applying magnetic field is that G mu B BMS. Here, G means that it is a gyro magnetic ratio or the Lambda G factor. Lambda G factor can be calculated in the quantum mechanics class, and I assume that you already know that the concept of Lambda G factor. Lambda G factor measures the strength of the spin and orbital angular momentum, and here in general, 3/2 plus S plus 1 minus L plus 1 over 2J plus 1. It is a Lambda G factor. Lambda G factor, it is the energy of an electron spin on the magnetic field B field, on the B field. In a single electron, the Lambda G factor is about the approximation is that the 1 plus alpha over 2 pi plus and so on. Alpha means that this fine structure constant 1 over 137, and therefore it is close to 2.002 in electron. It is very close to 2. Therefore, in the Lambda G factor of electron is 2, and also spin is plus minus 1/2. Therefore, the energy of electron is about the plus minus mu BB. We call it as a Zeeman splitting, Zeeman energy. When there is a single degenerated energy state, when you're applying magnetic field, one spin up and spin down has the mu BB energy, and also 1/2. And I'm sorry, it is plus 1/2 and minus mu BB. Therefore, we call it as a Zeeman splitting. Here also we we should take into account the angular momentum, and total angular momentum is that in quantum mechanical representation H bar L, in classical point of view, is that for respective electrons and Ri cross Pi, it is a quantum classical point of view. It is the summation means that for overall electron. In this case, let's consider for the Hamiltonian in the G electronic system. Hamiltonian in G electron in an atom. Here the H0 means that without applying magnetic field, and because there are G number of electrons, and when you consider for the electronic states, and there are G number of electron, therefore let's consider for the for each electronic state, and because electron mass is same, therefore Pi square over 2m plus Vi. Vi is the potential energy of potential energy between electron and ion. Here we should employ the applying magnetic field. On the magnetic field, and because we already know that divergence B equal to 0, therefore we can define that because any color of divergence is equal to 0, therefore we define that the magnetic field like a color A, where A is a vector potential. In many cases we choose that choose the magnetic vector potential as a gauge invariance, and also here let's define that magnetic vector potential L A is represented by the 1/2 B cross R, and anyway you can I do not describe in detail why we use this magnetic vector potential, because if we choose this magnetic vector potential like this representation, it satisfy the call A can define that the magnetic field and also divergence of magnetic field is also 0, or already satisfied. And anyway, then this means that it is a Coulomb gauge in many cases, and Lorentz gauge or the Coulomb gauge, and momentum can be the plus canonical. We call it as a canonical momentum, and magnetic vector potential can be defined like this. It is Lorentz gauge or the Coulomb gauge. And anyway, then it is simple to understand in the conventional electricity and magnetism class, and it is also basic representation of the Coulomb gauge. And here when we substitute this Lorentz gauge into the Hamiltonian, and here let's define that it is not H0 but H. H means that we are applying magnetic field. Therefore, here summation to 1 to G number of electrons, and also P square should have the Pi plus EAI, and is a function of Ri, and it is a square. It is a canonical momentum square, and plus potential energy Vi. Anyway, it is also Ri function, and also additional Gman energy is that G mu B dot S. Here S means that spin angular momentum of electron. Here, and let's expand this relation, and the summation for I and the kinetic energy pi square over 2m plus vi, it is h0 without applying magnetic field, and the additional term should be considered, and I, and here anyway, 2 cancel with each other in the denominator and the numerator, and the EPI dot ARI, and also plus, and the E square A square. It is a vector. And also G mu B dot S is magnetic field energy. Here we should calculate the term on this second term. Here let's calculate P dot A. In this case, and Pi dot magnetic vector potential is that the 1/2 B cross Ri. Magnetic field is applying field parameter, that therefore it is irrespective of the single discrete electronic state. Therefore we do not there is no need for the subscript. And here because dot product and cross product can be exchangeable, therefore 1/2 B cross Ri dot P, and it is that 1/2 B dot Ri cross Pi. As you know, it is angular momentum. Therefore, it is angular momentum is represented in here like this. Total angular momentum has this relation. Therefore, it is that half h bar over 2 B dot L. And also, in the third term, should have the A square. It is that 1/4 B cross R dot B cross R. Yeah, anyway, and let's summarize. The Hamiltonian is that H0 is the Hamiltonian without applying magnetic field, and the plus, the second term is that plus summation for I, and E h bar over 2 m, and also B dot L. And here the third term is that 4 summation for I, and 4 and 2 multiply 8m E square over 8m, and B cross Ri square, and also plus applying field energy mu B dot S. Therefore, here can be write down H0 plus. Here it is a Bohr magneton can be defined in previously. Therefore, when we define that Bohr magneton, and anyway lie Bohr magneton and L plus, it is a Bohr magneton L plus. It is Bohr magneton L plus from the here L plus G mu B extracted in the outside, and the GS dot B, and also plus E square over 8m summation for I B cross Ri square. Therefore, here, this is without applying magnetic field, and here this term contains for the angular momentum and spin angular momentum. Here, this term we call it is paramagnetism. It describes the paramagnetism, and the final term it is a diamagnetism term. When from this Hamiltonian we can understand that the paramagnetism and diamagnetism, we do not take into account the interaction between ions, and just only the interaction between the interaction between spin and the outside magnetic field. Here, therefore, let me think about in detail. Before we start interpretation of paramagnetism and diamagnetism, and we should understand the dimension of the magnetic in magnetic materials. And here we define the magnetic susceptibility dimensions in magnetic susceptibility and magnetization. From the electrostatics, you know the magnetization. Magnetization is defined by that the magnetic moment divided by the volume of the materials, and the magnetic susceptibility is defined by that the magnetization has a linear relationship with applying magnetic field. H is the applying magnetic field, and M is that magnetization, and therefore the magnetic susceptibility is that here definition, and the M over H. Therefore, because it is a vector divided by the vector, and this magnetic susceptibility basically is a tensor quantity. The dimension of magnetization, therefore, dimension of magnetization is that magnetic moment EMU. EMU means that elementary magnetic unit, and m square is the meter square. Meter square is the volume, and also applying magnetic field. Here it is a Weierstrass dimension. Therefore, the magnetic susceptibility dimension is that magnetization EMU per m cube, and the magnetic field Weierstrass. In other words, and the volume can be recalculated as a mass. Therefore, EMU per gram Weierstrass, whether meter square, can be write down as a mole EMU per mole Weierstrass. But we should care for the dimension when we measure the magnetic properties in experiment. And therefore, at first, when you measure magnetic moment, the measurement unit is the EMU unit, EMU. And here, in many cases, the magnetization unit should be changed as a Bohr magneton, because Bohr magneton is the elementary magnetic moment. And therefore, how to change the dimension from EMU unit to Bohr magneton is that here EMU is the measurement unit, and also molecular weight, and also Avogadro number, and Bohr magneton plus mass. Then it should have changed as a Bohr magneton unit, because here EMU and gram per mole, and also here per mole, number of mole, and Bohr magneton and gram. Therefore, it is therefore gram per mole can cancel with each other, and therefore it is mu b dimension. Here, the second case, in many cases also, EMU should have the Gauss unit in some cases, and in that case, EMU multiply density, sample density, and 4 pi mass. Then this dimension may have the EMU times gram per cubic centimeter in the CGS unit, and 4 pi gram. Therefore, it is that EMU per 4 pi cube centimeter, it is identical with the Weierstrass was the Gauss unit. We should remember in here. And anyway, here we used the CGS unit, not MKS, and the dimension change in electricity and magnetism is very complex, and also in some cases I also do not remember, and also I always check the textbook. Therefore, we should be very careful on the case. And third case, in magnetic susceptibility, EMU should have the EMU per mole Weierstrass order. It is identical to the 4 pi cube centimeter per mole. In this case, the EMU multiply molecular weight, and also magnetic field divided magnetic field times mass. Then the dimension may have the EMU times gram per mole, and magnetic field is Weierstrass and the gram. Therefore, the unit may have the EMU per mole Weierstrass. It is a unit for a conventional unit for magnetic susceptibility. Please be careful always when you do the experiment, and you should change the unit and be very careful to analyze correctly.